Top Med Talk. Hi, it's Monty Mython here, Editor-in-Chief of Top Med Talk. Well, these are extraordinary times. Despite all the challenges we face, we will continue to deliver free, open access medical education for as long as we can manage it, as well as our new regular updates on COVID-19, the global pandemic of coronavirus. Reporting from the front line, we'll be concentrating on enhanced surgical recovery. Why have we made that decision? Well, with an unprecedented pressure on resources, many institutions have decided to accelerate their widespread adoption of enhanced recovery. And why? Well, it's never been a more important time to reduce complications, readmissions, avoidable ITU bed occupancy, and to get our patients home fitter and faster after major surgery. As somebody who's about to get back into the trenches in critical care, to all my surgical, anaesthesia and perioperative care practitioners, thank you for making this a priority. A big shout out to our sponsors, in particular Edwards Life Sciences, who have very generously agreed to continue to support this resource, that's Top Med Talk, at a time of global need. We're all in this together. We will get through it. It's going to be fine.
Hello, I'm Joff Lacey and welcome to Top Med Talk and this our special series of podcasts on Xtreme Everest, the groundbreaking research program that for the past decade has pursued a novel approach to scientific exploration, performing large-scale healthy volunteer studies at high altitude to mimic the effects of critical illness, with the hope that their findings may be brought from the mountainside to the bedside and improve the care for our sickest patients. In these podcasts, we will take you through the story of Xtreme Everest, from its inception to its discoveries and to the future of this unique endeavour. I'm joined by Dr. Dan Martin, Research Expedition Leader on the second Xtreme Everest expedition, and summiteer on the first, so a well-qualified guest. Dan, many thanks for joining us.
No problem.
Now, Dan, you've been involved in many, if not all, of the studies in some capacity, but you have focused on looking at a particular type of blood vessel and how that changes with the hypoxic conditions of altitude, and that is the microcirculation. Can you tell us what is the microcirculation?
The microcirculation are the very smallest blood vessels in our circulatory system, so you can't really see them with a naked eye, so they're often forgotten about. They consist of three types of vessels. We call them arterioles, capillaries and venules. And this is where most of the transfer of oxygen and nutrients to the tissues that they supply, this is the sort of interface at where that occurs. It's a very, very important part of your circulatory system, but traditionally not studied very well, primarily because it's just so difficult to quantify the microcirculation. But in recent years, the technology has advanced so that there are camera devices, sort of microscopy cameras, whereby you can non-invasively look at the microcirculation and make some meaningful quantitative measures from it. So we've taken advantage of this leap forward in technology.
And why did you think it was worth looking at? If it's more difficult to look into compared to the larger blood vessels and arteries, why not just study those and get the information from that? What were the clues that microcirculation might be a key factor in how we adapt to hypoxia?
Well, both in intensive care patients and people travelling to high altitude, we noticed that if you look at normal measures of the circulatory system, so cardiac output, so how much blood is flowing around the system, oxygen content, so how much oxygen is being carried within the blood, there's not really any differences between the patient group who survive and don't survive and the people going to high altitude, those who are successful and those who are unsuccessful. So really the macro circulation, so the large vessels and what they transmit within them, don't really play, well, it's not they don't play a part, but there seems to be no differentiation between success and non-success.
So they don't have the determining role, so maybe further down in the final pathway of oxygenated blood might be the key.
Exactly.
And so you looked at the microcirculation on both expeditions, is that correct?
Yes, we did.
And so on the first one, what was the objectives? What were you looking at?
So in 2007, the first expedition, what we did was to use one of these microcirculation cameras to study ourselves. So lowlanders ascending to high altitude, just to see if there were any changes at all in the microcirculation, just really to determine whether it was something that's worth studying. We took the camera with us and we took it up as high as 8,000 meters, so at Camp 4 on Everest. and we looked at the microcirculation underneath our tongue, called the sublingual microcirculation. And that's not necessarily because we think the tongue is an important thing to measure, but it's just a very convenient part of the body, pretty non-invasive, where you can just place a camera and get really excellent films of the microcirculation.
And what kind of information is the film, the camera you're using, giving back to you?
So it takes moving images, like a movie, of the blood flowing through the vessels. So you can see individual red cells moving across the screen in these short clips, maybe 5-10 seconds worth that you're taking. You can then use software to analyze these clips. And the two main things that we look at really are how quickly the blood is flowing through the microcirculation, and the other is the density of the blood vessels. And so we can determine those and assign a quantity to those and then compare changes within people and between people.
And just to illustrate how impressive these images are, you can see individual red cells running through these tiny blood vessels. Is that correct?
Absolutely. So you can
remarkable images.
Yeah, you can. It's a very, very simple technology that you can just sit at a desk, put the camera underneath your own tongue, and on a nice big screen you can clearly see individual cells going across. It's an amazing window into your own physiology.
And so what did you find on that first expedition as you ascended up to 8,000 meters?
With the two measures I mentioned, so first of all, the flow, what we saw was that the longer we stayed at altitude and the higher we went, the slower the blood flow became, and the density increased along with that.
And was that what you were expecting? What do you think you would find on that first expedition?
Initially, actually, what we thought was that the flow may get quicker, because we thought the blood would be circulating around faster because there was a lack of oxygen in it, and we might see it speeding up. So we were quite surprised at first when we saw this very slow flow, and it's really quite marked when you look at it. You don't need to be very skilled or a scientist. When you look at these videos, it looks almost like treacle being squeezed through the blood vessels. So there's a lot of blood cells around, and it's a very slow, thick flow going through the vessels.
Not an efficient way to deliver oxygen.
Probably not, no. I mean, we can't measure the amount of oxygen using this technology, but it looks to be moving very, very slowly through the tissues.
And was that likely to be due to the fact that because you'd been exposed over several weeks and months to this high altitude, your body had done the very standard response of increasing its hemoglobin, the red blood cells, and that's why it was moving slower through the microcirculation?
That would be the best explanation. The study wasn't really set up to be able to answer that question, but certainly your hemoglobin concentration rises with altitude and with time, so that would seem the most likely factor causing that.
And so, again, in the second expedition, you looked at the microcirculation, but you had a slightly different approach this time. Tell us the difference with the second.
When we went back for the second time, we were intrigued to know whether or not there are any differences in microcirculatory flow and capillary density between us and the indigenous high-altitude population there, the Sherpas.
Because, worth highlighting again, they do not have an increased levels of oxygen within their larger blood vessels compared to lowlanders.
That's right. So
in fact, it's lower. Is that the understanding?
Yes. So if you compared them to us using sort of standard measures that we have, you wouldn't really be able to determine the difference between us or them. And as you rightly say, actually we have, as lowlanders, a very big response with our hemoglobin concentration increase. Theirs does rise a little, but it's almost nothing.
And so what were the findings with the Sherpas compared to the lowland residents?
So when we looked at ourselves again on the second trip, we could see, as before, we as the lowlanders had this reduction in blood flow and increase in capillary density, but by comparison, the Sherpas did not show this slowing down of the blood flow. So at the highest altitude we measured them, which was at Everest Base Camp, they had very rapid blood flow through the microcirculation, and if anything, it was slightly increased from their baseline measurements.
So this must therefore... Maybe, I mean, not proven, but this must be one of the key reasons that they are such high performers under these hypoxic conditions.
Quite possibly, yes. I mean, they also had much higher vessel density than us as well. So not only were the blood cells moving rapidly through the microcirculation, there was a denser network than we had as well. So arguably, they've got a greater ability to deliver oxygen at a micro level than we have.
To the cells themselves,
Absolutely.
Kind of the crux point.
Yeah.
And so I assume, as we know, that the objective of the Xtreme Everest expeditions are to translate those findings into improving care for critically ill patients in intensive care. So Can you expand on how you think maybe these findings might help improve the care of those sick patients?
Well, I think what it demonstrates to us is the importance of microcirculation in conditions where there are low oxygen levels. So when we look outside of this at other conditions, sort of pathological conditions that humans get at sea level, so maybe heart failure or severe infections, so sepsis, you see a very disordered microcirculation, this slow flow and very heterogeneous flow. So some areas fast, some areas slow. And this is almost always associated with bad outcomes in patients. So it's very interesting that what we see in the lowlanders is a slow flow, actually quite comparable to what you would see in a patient with heart failure. But the Sherpas are just not showing this. So they have a resilience in their microcirculation, which may well be responsible for, or at least in part, for their great performance at altitude. But I think what it shows us is, regardless of what you measure in the macro circulation, so things like blood pressure and oxygen saturation, if your microcirculation is not functioning properly, that's a hallmark of poor performance.
So if you can confer that benefit that the Sherpas experience onto critically ill patients, it might just allow their body to adapt to that physiological hit that they're undergoing and increase their chance of recovery. I suppose that's
It sort of reinforces the message to us that attempting to target the microcirculation rather than the macrocirculation in the critically ill is something that we need to put some energy into studying in the intensive care unit.
Because routinely now in hospitals, in intensive cares, we don't really objectively look at the microcirculation. It's not often a target, is it?
No. And whilst the camera I've described is a fantastic research tool, it's not quite there yet for sort of routine measurements in patients. There's quite a learning to do to get the technique working well and to get reliable results. And although you get these great images, you then have to go through the process of analysing them, which takes some time. So I think until the technology has advanced even more, such that even untrained people will be able to take a measurement and immediately get a value which is of meaning to them at the bedside, I think it's going to be very difficult to target the microcirculation at the bedside. But I think these things will come in time. Now we've learnt more about the microcirculation, but the technology just needs to catch up a little bit for it to be effective at the bedside.
Dan, that's all we've got time for, but thank you very much for talking to us.
My pleasure.
You can find the rest of the podcast on our website, www.topmedtalk.com, and you'll find plenty of other material embedded there for your interest. That's it for now. Thank you for listening, and goodbye.
Top Med Talk.